here we have our solar system. I also have an app called Space Engine. That's pretty cool. I guess we're just going to replace different stuff with our sun. So let's go ahead and pause the simulation. Here we are. There's the sun. Let's replace the biggest star in our solar system with the sun. So let's go and search Stephenson 218. Sorry, I was too lazy to create like a screen recording. Here's Stephenson 218, and oh my goodness. This would be where Stephenson 218 would be, and holy gosh, it is bright. Alright, now let's look at it. Oh my god. Look at how big this thing is. This is it compared to our little poor sun here. Earth is engulfed, Mars is engulfed, some of the planets just said goodbye. Or actually, that's Eris. Let's see where Uranus is. Uranus is just chilling over here. It's negative 222 degrees Celsius. It's not going to be for a while. Or at least it's going to... Why can't I talk today? I meant to say that it's not going to be negative 222 degrees Celsius for that long. This is Uranus right here. You can turn around. You can actually see the side that's facing the sun. So this is kind of like the new Mercury, because I think Saturn even is engulfed. This is Stephenson 218. This is how big Stephenson 218 really is. Its luminosity is 4.4 million times. I think that says 4.4 million. Does it say 4.4 million? 444. Actually, I think that says... Oh, no, never mind. That does say 4.4 million. It is 4.5 million times brighter than our sun. Wow. And they make solar eclipse glasses specifically so that you can't look at the sun, or you don't have to. Imagine if you saw something 4.5 million times brighter than our sun. In order to watch a solar eclipse safely, you would need to wear 4.5 million solar eclipse glasses at the same time. Here we are back on Stephenson 218. Its speed is 21.5 kilometers a second. That's actually relatively slow. And its age is currently 0 seconds because I have my time paused. This is what it looks like from 56 astronomical units away. 57 actually almost. This is what it looks like. It's a big ass ball. That's what it looks like. And guys, guess what? Because it's that big, because one astronomical unit is the distance from us to our sun. Okay? This is what it looks like when we're a distance that's 57 times farther than the distance from us to our sun, and this is what it looks like. Alright, so in order to be as big as what our sun looks like, we need to go 537 astronomical units away, which could mean, actually, even that's not far enough away. About 1,000 astronomical units. I know that doesn't say 1,000, but it still says 767, and that's still a lot. That means it's about that many times more big than our sun. Let's go to its size. Bro, why can't I find size? Okay, so it's a radius. Radius is well, you can see it right here. Radius is the circle, it's basically half the distance of something's diameter. So that means it's 10 astronomical units in size. Okay, we need to go about 1,000 astronomical units away for it to be about the size of our sun. So even this is a bit bigger than our sun, okay? So 10 astronomical units, that means its actual diameter would be about 20 astronomical units. That's 20 times bigger than the distance from us to our sun. And as you can see, you could see it from over here, if you couldn't already tell. Oops, let's get away from Uranus. So let's go to Stephenson 218. This is hard. Look at how long it takes to get. Okay, never mind. So yeah, that's the distance. Oh my gosh. So that is the distance from Earth to our sun. This is the size of Stephenson 218. Because the time is paused, there's no catastrophic damage that can be made. So let's delete Stevenson 218. And the solar system is back to normal with our good old star. Okay, let's get off delete. And let's go to our star. Oh my gosh, it is so much dimmer, so much smaller. It is 1 astronomical unit in size. That's pretty interesting. All right, let's go to Haumea. Why I want to go to Haumea is because Haumea is a dwarf planet, and it looks like an oval. So this is Haumea way out in here just chilling. Okay, so it looks circular from over here, but in real life, it looks like an oval. Like, let me just go to my top browser, Firefox. Also, check out my Discord, anyway. Actually, let's look up Haumea. This is Haumea right here. Look at this. This is what it looks like. It actually has a ring and 2 moons, apparently. Bro, my internet is the slowest thing in the world, and snails think they're slow. Anyway, this is Haumea. And it's a complete oval, but on Universe Sandbox, and probably even Space Engine, if you look at Haumea, it looks like like a circle. This is the brightest part of the planet. Yet it looks so dark because it's so far away from the sun. It's negative 234 degrees Celsius. Its orbital period is 283 years. 283. Yeah, negative 234 degrees Celsius. Its radius. So that means that its radius, that its diameter is probably about 19% the size of Earth. Let's go to the surface. So the surface, so yeah, as you can see, the hottest is negative 234. The coldest is negative 234. Okay. Sea level, let's see how hot it is in sea level. Okay. Let's see what it's composed of, what it's made of. So it's made a lot of iron and silicate. Okay, interesting. Okay, that's not. So let's see what the view would look like in daytime. Oh my god. That actually looks pretty cool. Like you're actually like kind of like high above the rest of the solar system. That's the asteroid belt right there. You can see the different names of it, like 704 whatever the hell, however you pronounce that. There's Uranus just chilling down there. Let's see if you can find Earth. Okay, so, oh my god. So Haumea is so far away. So this is Haumea. This is the lightest part of it. Okay, so we are so far away. So look, that blue line, that's Earth's orbit. My gosh. That other orange one, I suppose that's Mars. That's Uranus and Neptune just chilling over there. There's Chiron. Okay. Eris is actually really far away. So this is Eris. It takes a while. All right, there we go. Okay, this is even farther. This is even further, guys. You can't even see the light, man. It's always nighttime. Okay, anyway. The Earth is probably way down there. And there's Haumea over there just chilling. This video is almost over, at least part 1. We'll make part 2 in probably like a minute. But this is Sedna. It's a dwarf planet that orbits our sun. And look at what its orbit is like. It is so goofy. Look at this. It goes way out of our solar system, all the way out to here, and then it comes back. So it's kind of like in and out of the solar system, like way out far, like way. And you can see that it's negative 243 degrees Celsius. Let me expand this real quick. So you can see that it's negative 243 degrees Celsius. That's about the temperature of Haumea. But it gets real cold when it gets out in the solar system. Like negative 273, that's the coldest part of our universe. Way outside any stars. Also, apparently, they believe that there's a planet called Planet 9, which orbits the sun at a very far distance. You may be wondering what this is. It's kind of like an asteroid, maybe a planet in our solar system. It's called C1906E1. This is it right here. And look at its orbit. Look, it goes like from here to the sun. Wait a minute. But then this is also its orbit. So this is the C's orbit or whatever. It's this little line. You can see it, right? Yeah, you can see it. And it goes all the way out to here. This is the end of something in our solar system's orbit. And you can see we can go to the sun. And the distance to it, let's go to the end, very end of its orbit. Like the tail end. And if you go to oh my God. It literally says 56563761 our galaxy. I don't know what that means. What's our galaxy Milky Way radius? So what's that number? 565,63761. That's 56 million. I think there's something in our solar system that orbits at farthest 56 million times farther than the galaxy. 56 million times, that's like pretty much the end of the universe. Our solar system truly is spectacular. And let's go back to the sun. Here we go to the sun. Oh, snosh. Oh, fuck. Oh, snap. Okay, we're getting close now. Okay, it went farther again. Because I always say farther instead of further. Q&A, or not Q&A, poll. How do you say further? Like further or farther? Let me know. The closest planet to the sun is Mercury, as we all know. Here it is right here. It looks exactly like our moon. And it's also about the size of our moon. It's about 60% or maybe 76% the size of our Earth. 38% is the radius. So this is Mercury, and this is how big the sun appears to look when you're at Mercury. So it would look like about this. If you saw your sun, if you saw the sun in our sky like this, you'd be living on Mercury, man. Pretty good stuff. All right. Let's try to create a solar eclipse with Mercury and the sun. All right, that's kind of like an eclipse with our sun and Mercury. Like if you were somewhat away from it, an eclipse would look about like this. So that's pretty cool. Let's go to Earth. Earth would look pretty cool from over here. So here we are, our God's green Earth that we live on right now. Its average temperature is 7 degrees Celsius. And I'm going to go ahead and add the moon. Our moon would orbit about here, maybe. Our moon is about 384,000 kilometers away. So this is probably about what our Earth would look like. I think that's how our Earth would look like. So let's click on Earth. Here we go. This is Earth's info. And the distance to us right now, how far away it is, it says 0.00371 astronomical units. Because it's 100 times further away, I don't think that's 100% accurate. That would be like what? We are way too far away. I think we have to be like 384,000 kilometers away. I guess we'll just simulate how it orbits. So let's play this simulation. Okay, it's orbiting pretty smoothly. This is 16 days a second. As you can see, each second that passes by, 16 days passes by for the simulation. Also, it means that in about 30-something seconds, a year passes by. Yeah, the moon's way too far away. That's what the moon looks like from us. But that's not to scale. We gotta make it a lot closer than that. Here's some information. Betelgeuse is about 700 light years away. So let's go ahead and add Betelgeuse. And what we're gonna do is we're gonna watch it explode, because scientists estimate that it's going to explode in not too long. So how far away do we want it to be? Want it to be 700 light years, about 600 maybe? Let's just make it 654. Again, it's not 100% accurate, but this is about how far away Betelgeuse would be to the sun. So let's now go to the sun, and we should see Betelgeuse in our sky. It's just going to take a while to find. I'll catch up to you when I find it eventually. Okay, so it's right over here. Okay, so let's go ahead and explode that. Let's go ahead and go all the way to Betelgeuse. All right, here's Betelgeuse. Okay, we're at Betelgeuse now. I wonder how you explode it. Let's try making its mass bigger. Or actually, you know what? I have a good idea. Let's do this. I'm ready. Let's add a bunch of suns. Yep. Sorry, Betelgeuse. We're adding a bunch of suns to yourself. And we're going to simulate you exploding into hazardously very bad, no good soul. I don't know. I'm adding as much as I can. You can see how fast I really am clicking. I'm very slow. That's why I need a... Okay, my game is freezing right now. It seems like oh my god, I already added some of that other stuff. But let's slow down the simulation and see how it would look like in real time. So let's just go ahead and do 1 second. Okay, 1 second, here we go. So, oh my god. If you can't already tell, my game is glitching out like absolute fuckery right now. It's freezing like a computer in 2001. Let's just go to the sun. So that's how crazy the explosion actually would be. Let's go to the sun. Let's go. Actually, to make it even more like accurate, let's go to Earth. Come on, Earth. But I feel like an old grandma who's on the computer right now. All right, I'm ready to play the simulation now. Oh my gosh. That is brutal. That's the Betelgeuse explosion in the distance. My goodness. In case you wouldn't able to already tell, my game is glitching, but also it would be insane. Like that looks like a completely separate star over there, and that's in real time too. 1 second per second? That's real time. For more notes though, let's speed up time. To give you a glimpse, I just made it at about 90 seconds per second. And you can really see it flame now. Look at that, guys. Let's speed up time even more. We're talking this fast, where we see the Earth rotate like that. So it seems like not much would happen other than that turning out like an entire star. And I guess that's how it would be like bright. Vsauce said it would be like another sun. We are ready for some interesting stuff about space. So basically, this is a flashlight, but we're going to use it as the sun. This is what the recent solar eclipse looked like. So this was the sun, and I'm going to use a penny as the moon, and we're going to cover the sun with it, and it will eventually look like a ring of fire. Again, I know it's not 100% accurate because my finger's in the way, but this actually does kind of look like the sun. You can't lie, come on. And this is a solar eclipse. Doesn't it look accurate? This flashlight is pretty bright, quite a few thousand lumens, so it does look like the sun. And then we're going to use this as the moon to cover it. And that really does look like an actual solar eclipse. And this all happened in April 2023, or not 2024 actually, April 8th. Yeah, I am way too much. I am way too old. I still think it's 2020. Anyway, let's imagine the moon was closer. Actually, this is the light it would spread, which would look very similar to the actual eclipse, which would also look cool. Let's now pretend or imagine that this is that the moon was a little bit closer. How dark would it actually get? Well, let's just imagine this is the sun. And we're going to use a more accurate representation of the moon. Here it is. It's pretty cool because, though it's not plugged in right now, this is an interesting representation of what the moon would actually look like. Let's imagine the moon was closer. The sun is like this and the moon is like this. The moon would eventually cover it, making all of the light on this. By the way, what's cool is that you can use a flashlight, put it on the other side, and reflect the moon. Once again, the light needs to be completely off and stuff, which it is. This would be the sun. And you know what? Let's even make the moon a little bit farther too. See how the moon completely blocks the sun. If it were closer, then it would be even crazier, getting even darker than it should be. Here's an example. Let's use the same penny we used earlier. If a solar eclipse existed like this, it would actually be this dark since it fully covers the sun. And interestingly enough, this is about the distance you'd have to be, like the flashlight to the camera, to have an accurate depiction of the sun. Meaning that because the penny is exactly this size and it's completely overlapping, this is kind of an accurate representation in not a lab but my own bedroom of a simple solar eclipse. And the light that flashes on is the shadow coming from the moon, which is why solar eclipses get so dark. And because it fully covers it, you could say that even if the moon were bigger, it may only get a little darker, and that's because the moon already fully blocks the sun. This is the sun. This is the moon. Blocking it like a solar eclipse, it's already about this much covered. But it still looks like the normal sun. It's only when it gets fully covered that you can see the corona, the almost scary representation of the sun. When it's directly pointed, it looks even crazier. That's where you're in the major part of the line of totality. Also, I wanted to say that there was also another solar eclipse in 2017, and that same eclipse occurred, but it wasn't as total as before, and not a lot of major cities lied in there, which is why this solar eclipse that just happened about a month ago almost was so significant. I have a lot of fun making solar eclipse and solar system simulations a lot, especially when it's public. Also, do you wonder why it's getting brighter and darker? You can tell by that light back there. I'm using the flashlight as an accurate depiction of what I would look like if the day was sped up. When it's below, the sun is completely set and it's night. When it's completely above you, it's bright. And etc., etc. And here's a cool reason or simulation. This is the reason though. So this is a simulation of why the moon appears bright in the night when in reality it's just a rock, not much brighter than this. Well, it all has to do with the sun. You see, when the sun is near the moon, like especially when the moon rises, it's also brighter, making it more significant, which is actually one of the reasons why it becomes brighter and bigger. It's the reasun why it appears bigger. But at the same time, there's supermoons that make it appear even bigger. Anyway, that's not the point. Right now, it just looks like a rock. But when I put the sun in front of it, boom. I call it the sun because we're seeing it as just that. Now I have to put it right up to it like this because this isn't nearly as bright as the sun. Like, yeah, it's bright. It's a powerful flashlight, but that's still not anywhere near the brightness of our sun. Just a split second looking at the sun and permanent eye damage can occur. That's why you have to be careful during the solar eclipse. Also, I don't know why I'm saying that because the solar eclipse already happened like nearly a month ago. Anyway, so yeah, that's why the moon appears bright. Now it doesn't just look like a rock. It looks like a rock that's infected with friggin' uranium or whatever. It's the same reason why my face appears brighter when I do this. Also, from here you have a good view of what sunsets are like. That's an accurate depiction of sunsets. This is the sun when it's high up. This is the sun going down. And when it gets below our sight of vision, it becomes dark and it becomes what we now know as night. It's kind of spooky, really, to think about until you realize that it's just the solar system. And it's completely natural. Also, this doesn't actually have to be just the sun, as there's a lot of other suns and stars in our galaxy and even our universe. Also, when I point the flashlight closer to the screen, you can see more and more of the flashlight, and the actual light is right here. That's because only some of the sun's light actually is visible. Believe it or not, even using things like binoculars, don't attempt to do, except if you're using solar eclipse glasses and you use binoculars as well, through telescopes and also even like stuff like that, you could see the sun more detailed. And that's because you appear closer like this. I swear if I could use a telescope at this flashlight, it would appear more detailed. But because we're slightly far away, there's no real way to actually see that beautiful detail is. Unless you get super close or you're really zoomed in. Of course, there are things like sunspots that we can't just see with the naked eye. It's kind of depressing. On the other hand, though, you have beautiful sunsets and sunrises that people adore in life for romantic moments and Instagram photos. Sunsets and sunrises are a miracle, and it's all thanks to God. He created the universe. However, still, same goes with flashlights. Yes, a simple flashlight. And if I point it out in the night sky, it even lights up things like bushes, which is pretty interesting. I wanted to sponsor Wix in today's video. It's a great website where you can make websites yourself. Now look, I don't got time to be making a sponsor on a freaking TikTok video that's only 10 minutes long on a sponsor. But anyway, I wanted to make part 2 of the space video I wanted to make. This is the sun. We're not going to talk much about the sun, actually. But we are going to be talking about our lovely moon. This is what it would. This is an accurate representation of the actual moon. Looks decent. And now let's talk about the moon. I'm going to put it at a comfortable distance so that it can feel more accurate, even though this isn't 100% accurate. So what I have to do right now is plug it in, so I'm going to catch you up then. You may be wondering to yourself, Eli, what is that light over there and why is it flickering? Well, it's one of those LED lights and it doesn't really work. It kind of flickers, but this is the moon and I love it. I'm just going to keep this flashlight on, mainly because I can see in the dark and I don't really know where anything is. So, this is the thing I use to control the lighting, and we can make it red just like a lunar eclipse. And this is what it looks like as red. Ready? That's what it looks like as red. This is what it looks like normally. This is what it looks like during a lunar eclipse. And lunar eclipses occur, you might already know it because it's when we are right in between the sun and the light we're seeing that's being eclipsed, the moon. I'm saying it's being eclipsed because technically for them, they're experiencing a solar eclipse. For us, let me show you how. So that's our moon right there. Let's imagine that this is the moon. You can pretty much imagine anything with the Earth. We could literally imagine that that this tape roll is the, yeah, why not? This is the tape roll, this is the Earth. And, you know what, let's actually make it, white. There we go. Okay, so, this is the sun casting its shadow. And you can see for them, you could kind of just imagine how for them it would be, hold up, it's gonna go. You can kind of just imagine how for them, this would be the sun and this would be the Earth. And the Earth would be blocking the moon and it would become red just as a lunar eclipse. And that's how lunar eclipses occur. They occur because the lunar eclipses occur because, like imagine this is the Earth, this is the sun, and the Earth is being casted into the moon, making it red, and we see it as red, and we think it's cool. Now here's a solar eclipse. We also talked about this in part 1, but we're going to talk about it again because I love you guys. So this is the sun. This is our beloved moon. We're going to use a penny, and we're going to overlap it over the sun so it looks like a corona, as you can see, right? Now, this is our moon about to overlap our sun. It's already this much covered. This would be the sun, but for some reason it still looks like a sun. How about cover it this much? Okay, yeah, this much. Okay, this much. It can still look like the sun. It turns out it does, but it's still less bright. It's only when it fully covers the sun that you can finally see the shaped corona, even if you're within distance. It's only when it gets a little bit further from the sun that you can finally see the thing like corona, and this would be the lighting source. Now, what I wanted to explain here is that solar eclipses actually happen very often. Look, though they may only happen here for every 1 or 2 decades, they appear in the world every 1.5 years. That's 10 times more often than we experience it here in the US. And this is it when it's this much covered, it still looks like a perfectly good sun. You probably not notice it the first few seconds, but this is the perfectly good corona of our sun eclipsing at the solar eclipse, and this is what it would look like up close or zoomed in. It would look normal. Now, let's pause. I know what you're thinking. Eli, it wouldn't actually look like this. There's a light bulb inside. There's settings and there's no way it would look. This is just a simulation and it's meant to be far away anyway. Anyway, the same situation also occurs when the sun sets, as this is what it looks like. Here's some context. So, a sunset's kind of like an eclipse of us blocking the sun. The horizon of us, our Earth, our beloved great Earth, God's green Earth, that blocks our sun. This is the horizon, the furthest of the Earth you can see. That's about 3 miles or 5 kilometers. And when that part of the Earth blocks our sun, this is what it looks like. And we call it a sunset. And that's kind of like an eclipse. And when the eclipse ends, it looks like this. A sunrise, except this is not that accurate because sunrises would occur from the other side. It would look like kind of something like that. Now, this is a solar eclipse. when the moon covers the sun, it looks like this. A beautiful corona, a beautiful croissant. It starts with a beautiful, circle or ball. Then it goes to a beautiful croissant. Then it goes to a beautiful hangnail, and then a beautiful ring. That's just me being silly with it. But this right here, what you're looking at, is the shadow being casted onto the earth while a solar eclipse is happening. Yes, that's the shadow being casted onto the earth while the solar eclipse is happening. This is where it's daytime. So this circle, I know it's not 100% accurate because it wouldn't actually spread this widespread. But guys, this is the daytime part of it. And the shadow would appear, maybe not like this, but at least a good chunk of the daytime portion, though looking like this in the night sky, blocking almost 100% of it, making it look like a ring. While I say almost, I say it because it never actually covers the entire thing. You may be not in the line of totality, you might be like 99.8 or whatever, and it might look like something like this, or like this. But that's okay. That's perfectly normal compared to some people. You see, this is the sun, this is our beloved moon, and it covers the sun, right? Notice how I know this is not accurate, but look, solar eclipses always look like this pretty much, like a ring. They call it that because only the corona and a lot of the sun is visible, making it look like a ring. It doesn't just look like the moon. If it was totally covered 100%, you'd see nothing. The sun would just disappear. It wouldn't just be completely covered up. No. It would completely appear to be disappearing. And also, this kind of, like, you see this, like, thing that looks like ground? Yeah, the shadow. This is kind of makes it look like a telescopic view of a sunset. And then, for a beautiful sunrise. So, yeah. When it's the middle of the night, it looks like this. When the sun is setting, it looks like this. When it's the middle of the day, it looks like this. And I know I'm talking nonsense, but it's just facts. It's just astronomy, and it should be known by everyone. I know I'm quite of a nerd, but come on, it's just knowledge. But if you don't know it, that's okay. The perfect way to see a solar eclipse is through solar eclipse glasses, but I have an even better idea. What if we use a shoebox, put the camera of this phone over it, and then use solar eclipse glasses and put it over the camera, then use an app called XZoom to zoom really far into the sun, and you'll get a really cool sun view. You might even see the sunspots. Well, turns out I don't even think we really need a shoebox, as there's a lot of other things that can cover the light as well, such as a tape roll. Lab science found that in an average laboratory or museum, sunspots carry through the way of a simple tape roll, even though it's not that used. The study was conducted on January 12, 2022 by Robert Simpson, an Indonesian science and laboratorist who claimed the existence of the sun before it even existed. Like when the dinosaurs roamed the world, the sun changed only 1% of it, meaning that because it's so old, it may not be 4 billion, but rather 6 billion years old, meaning that the end of its lifestyle could actually be sooner, more like 1 billion years. Let's go outside where there's more stuff outside where we can see an accurate representation of the sun. My annoying neighbor was mowing the lawn, so I had to wait till he stopped. I'm sure you can see it is very cloudy outside, but this will still work. The sun is about in those clouds, and I think it's actually starting to shine out. Anyway, I got back inside just because I want to try this again. I got solar eclipse glasses and a tape roll. I could use a shoebox, but I'm just testing if this will work also. I'll use a shoebox at the end of the video, maybe. Ignore the annoying sound of my neighbor. If you're wondering what this is the sun through solar eclipse glasses, but you can see too much, man. Like, it literally doesn't look like anything. These are the solar eclipse glasses I use. Alright, here I am from 7 hours later, and I let the photos flicker. I used the shoebox, solar eclipse glasses, and the phone I'm using to record right now, and I let the photos flicker. And these are the photos I captured. Of the sun. When I first took the picture, it looked like this. Then I took this picture after it flickered, And let's just say it looks like the coolest thing ever. You can see like the sunspots, you can kind of see the clouds blocking it. But I think that this one was by far the best because it's a more accurate representation of what the sun actually looks like. This sun literally looks like the sun in real life, but you also have details like sunspots and not even clouds either because there's not enough. This photo I took 6 hours to flicker and 1 hour to adjust the exposure. Now it's time for the second way, yes, the second way to capture the sun. And I have a probably even better way that's quicker, faster, and looks better.
Watch this.
Right now we are using an R22 motion camera which detects the motions of the sun, and through this you can't really see much, but you can see the exposure of the sun through the little bulb in there, and I love it. This is the setup right here. It has this little screw which you can turn and adjust the lighting. Besides though, I'm going to show you the images right after it's taken. It's an exposure camera. It works better than most telescopes, and you can see better images of the sun than other telescopes, cameras, etc. It's also great for long distance viewing. I have it on record right now. As you can see, it's on, and it has the setup right here. Sorry for my annoying neighbor again. But look at this camera. It looks majestic. I can't interfere with it. I think I might have said that. I'm not sure. But this is the front camera. I don't want to interfere it because it's currently capturing the sun at a low distance viewing, meaning that the sun captured will be very detailed, and honestly, this is quite zoomed in too, like 1200x zoom. The sun is captured at a 2 distance angle, meaning that it's approximately 92 degrees relative. My neighbors are the most annoying thing in the world, and babies think they're annoying. So my neighbor's still at it, but I think I just got the perfect sun view. And the sun has officially set, meaning I got the sunset as well. Check this out. So the camera I can interfere with now so I can show you the little details. It looks very stunning. Sorry, I'm getting carried. Alright, so this is the image I captured of the sun through my amazing telescope. This is only a photo. Watch what happens when I show you the video of the sunset I captured going down beyond the horizon. This is the video I captured of the sunset going down below the horizon. Isn't it cool? The sun's just going below, and that's the ground too. It was kind of like on a tilted angle, as you could see. And isn't that just amazing?